In this experiment, we explored the behavior of static friction and investigated whether it depends on either the surface area of contact or the weight of an object. Friction is a tangential component of the contact force that resists the initiation of sliding between two surfaces. For an object at rest, the frictional force adjusts itself as needed, up to a maximum value to prevent motion. This upper limit is called the maximum static friction and is bottled by the expression F equals mu times N, mu being the friction component, and N is the normal force exerted by the surface. Because the normal force on a horizontal surface is equal to the weight of the object, N equals mg, the static frictional force should increase proportionally with mass, but not depend on the surface area of contact. Classical friction theory predicts that for typical solid surfaces, the coefficient of static friction remains constant for a given pair of materials and is independent of contact area and moderate changes in pressure. In this lab, we tested these predictions by varying both surface area of the block and the mass of the block itself, measuring the force required to initiate motion in each case. Using these measurements, we determined the coefficient of static friction and examined whether changes in weight or surface area caused any measurable deviation from the expected proportional behavior. This experiment reinforces the concept that friction arises from microscopic interactions between surfaces and highlights the difference between theoretical models and real-world measurement uncertainty.
For this lab, the equipment we used was 4 wooden blocks, a ionometer, a wooden T-block, tape, a wooden ramp, and a metal track. The objectives of this lab were to find out if surface area, weight, and material have any effect on static friction and what the static friction was in different scenarios. In this experiment, we measured the mass of the block and slowly increased the angle of the board until the block began to slide, using that critical angle to determine the static friction and to test whether changing the block's surface area or adding weight affected the frictional behavior.
We ran this experiment 3 times. The first time, we kept the mass the same by using all 4 blocks every time, but we changed the surface area by changing the configuration of the blocks. According to the equation for static friction, the force only depends on the mass, which is in the normal force, and the coefficient of static friction. Since both of those are constant in this experiment, we should expect the friction force to never change. And here's our data. If we plot the angle in radians on the y-axis and the surface area on the x-axis, we should expect no correlation. Since a slope of 0 would mean that the surface area is changing while the angle is not, and our slope was just negative 0.00004, that means we did pretty good. Our absolute error was just 4 times 10 to the negative 5th. So we proved that surface area has no effect on the force of friction, but what about mass? That's hidden right there in the normal force. So to test for that, we can run the exact same experiment, but instead of changing the surface area, we can change how many blocks are stacked to change the mass. So here's our data. If we plot the angle in radians against the mass this time, you may expect there to be a higher slope, but it looks like there's not. What's going on? Well, yes, increasing the mass increases the normal force and therefore the force of friction, but it also increases the force of gravity pulling the block down the slope. So in fact, because these 2 factors are increasing by the same factor, we should expect no change in slope, and that's what we see. Well, to double check our work, we can look at the equation for the coefficient of static friction. By solving it for the critical angle, we can see that the critical angle is only determined by mu. So changing mass or surface area won't change this critical angle. But what is mu? Well, mu is just a scalar that tells us how strong the friction force can get given a normal force. And it's dependent on the 2 surfaces in contact. So let's find mu. Well, our blocks have a wood side and a foam side, and we have a wood track and a metal track. That's 4 combinations of contact surfaces that we can use to find 4 different mu's. That'll be enough to prove that mu depends on the surfaces in contact. For this last activity, we'll solve for mu by using the same mass every time and swapping out the surfaces every few times. we should be able to solve for mu because we can calculate the friction force using the angle at which the blocks fell. Well, that's a lot of data. But in the equation for the friction force, there's only 3 variables. So to solve for mu, we just need to divide the friction force by the normal force. To find those, we can just use the other data in the sheet, like the constant for gravity, the mass of the block, and the critical angle. We did 4 trials for each material combination to get our answer more accurate. After taking an average, we can see the coefficient of static friction to be these values for each combination. It seems that the foam was the stickiest material and the metal was the slippiest. So Ethan, do all these numbers mean that the equations were right?
In conclusion, our results supported the theoretical model of static friction, showing that the angle required to initiate motion depends primarily on surface quality and not the surface area of contact or the weight. When we changed the surface area of the wooden block, the critical angle at which the block began to slide remained nearly the same, indicating that surface area has no measurable effect on the coefficient of static friction. This aligns with the classical prediction that friction is governed by microscopic interactions between the surfaces rather than the macroscopic area exposed. By adding more weight, we were able to confirm that the normal force increased proportionally with the friction coefficient. Therefore, the block broke static friction at about the same angle. This measurement matches the relationship mu equals tan theta critical, where mu should remain constant while the maximum static friction force increases proportionally with the normal force. Small deviations in our measurements likely arose from inconsistencies in the ramp's surface, slight delays in identifying the exact moment motion began, and minor variations in mass measurements. We also found the coefficient of static friction of different masses, surface area, and the surface quality, and we found that changing surface quality did have an effect on this coefficient of static friction. Overall, our findings confirm that static friction is independent of surface area, but proportional to weight, and our experimentally determined coefficients of static friction were consistent across the different trial conditions.